Hi, my name is Angun Yang. I'm from Department of Material Science and Engineering at Northwestern University. On behalf of my co-authors Zhongyang Li, Michael Knudsen, Alexander Horin, Weijia Wang, Professor Corey Adin, and Professor Terry Oldham, I'm pleased to present our recent work titled Unidirectional Lasing from Template-Stripped Two-Dimensional Plasmonic Crystals. Laser light amplification by stimulated emission of radiation has been widely used in both research and industry. A laser consists of a laser cavity, active medium, and pump source. Due to the diffraction limit, the laser cavity is usually much larger than half of the wavelength. In recent years, people have been trying to shrink the size of the laser down to nanometer scale by taking advantage of surface plasmons. Surface plasmons are coherent oscillations of electrons at the interface of metal and dielectric. When light couples into surface plasmons, the resulting electromagnetic wave is called surface plasmon polaritons. There are two types of surface plasmons. One is propagating surface plasmons, which are supported by a metal film and provide light confinement in the z direction down to tens of nanometers. The other type is localized surface plasmons, which are supported by discrete metal nanoparticles, providing three-dimensional light confinement at a deep subwavelength scale. The bottom left image shows early designs of plasmon lasers. In a semi-conducting nanowire is sitting on top of a metal film, separated by a dielectric spacer. Surface plasmon polariton is propagating between the two faces of the nanowire, confined in the dielectric layer and providing the lasing feedback. B shows a gold nanosphere surrounded by dimolecules in a silica shell. The oscillating localized surface plasmon, supported by the gold core, provides the lasing feedback. In these two examples, the size of the laser has been significantly decreased, below that of the diffraction limit. However, meanwhile, we lose the directionality of the lasing emission, in contrast to the conventional laser, where emission is highly directional. In these plasmon lasers, the lasing emission is scattered out of the cavity with a limited directionality. To resolve this challenge, we and others have been using arrays of plasmonic resonators to achieve directional lasing emission. For example, C shows arrays of gold nanoparticles surrounded by dimolecules which show directional laser emission normal to the sample surface, but still the emission is bidirectional for these plasmonic arrays. In this work, we design a plasmon laser based on two-dimensional plasmonic crystals with the unidirectional laser emission, that is, laser emission into a single direction. The structure we propose consists of a metal film with arrays of posts on top. As will be demonstrated later, the metal film supports an SPP mode as a lasing cavity, and the post array concentrates electromagnetic fields and facilitates the lasing action. More importantly, the post array confines the lasing emission into two directions, while the metal film behaves as an emitter as in conventional lasers. As a result, the device will have a unidirectional lasing emission. To fabricate gold plasmonic crystals, we use a combination of phase-shifting photolithography and template stripping technique. Briefly, we pattern arrays of photoresist posts on a silicon wafer, deposit a thin layer of aluminum, and remove the photoresist. The aluminum naturally oxidizes to aluminum oxide and serves as a highly selective deep reactive ion etch mask. After deep etching into silicon, we remove aluminum oxide and deposit gold. The last step is using a curable polymer to strip out the gold. Both the scanning electron microscopy and the atomic force microscopy images show ultrasmooth surfaces for both the post array and the metal film. Compared with the as-deposited metal film, the stripped film has a sub-nanometer roughness, which can significantly suppress the loss of the system and is important for plasmon lasers. The SPP mode was characterized by an inverted optical microscope equipped with a spectrometer. The experimental SPP mode was observed at around 882 nanometer, which was in good agreement with the finite difference time domain simulations. On resonance, the near field exhibited a characteristic SPP wave pattern, with a large field enhancement around the post array. We use DMSO as a dielectric environment because it is a common solvent for dissolving dimolecules. We coated the substrate with the IR140 in DMSO and covered it using a nice piece of glass. The sample was pumped with an 800 nanometer femtosecond laser, and the emission spectra were collected normal to the sample surface. We found that the laser emission was detected at the SPP resonant wavelength and was confined to a beam at far field with a small divergence. More importantly, as shown in the bottom left figure, we proved that the laser emission was unidirectional, coming only from the post-array side. We conclude that the plasmonic crystals can combine the advantages of nanoparticle arrays and metal film, and confine the laser emission into a single direction. In this slide, we show that 2D crystals can screen how structure and material of the unicell affected the lasing response. Besides the stripped gold posts, we deposit gold nanoparticles onto stripped gold film. We stripped pyramid arrays, and we deposit titanium nanoparticles onto stripped gold film. These samples cover different features, including roughness, shape, and material. We performed lasing measurements and found that the stripped gold posts showed the best lasing performance. The deposited gold posts also had a lasing emission, but with a wider line width. The pyramid arrays only exhibited amplified spontaneous emission. The deposited titanium posts only showed a slight enhancement of the PR intensity. We conclude that in order to achieve the best lasing performance, the 2D crystals need to have a smooth surface and cylindrical shapes as well as strong plasmonic materials. We examined gold plasmonic crystals by simulating its band structure. We found that the band structure matched well with both the experimental results and the plane wave simulation. The modes in the experiments and the plane wave simulation were in good agreement with the SPP modes calculated theoretically, which were denoted by the lines in the top right figures. This indicated the SPP modes were the dominating modes in the system to which the diemolecules can transfer their energy. We further characterized the polarization state of the laser emission. To do this, we pumped the system with two different configurations, transverse magnetic and transverse electric. We put a linear polarizer in between the sample and the spectrometer, and rotated the polarizer in each pump configuration to record the output lasing intensity. We found that for TM pumping, the emission was preferentially polarized around 0 degree, which matched with the corresponding SPP mode. The same was true for TE pumping. This confirmed that SPP mode is the lasing cavity. Based also on the study of the post in the last slide, we conclude that SPP wave coupled with the post induced large log field enhancement and enabled lasing action. Lastly, we showed that the 2D plasmonic crystals serve as a platform to test different material combinations for both the cavity and the game. We fabricated silver plasmonic crystals and observed lasing emission at its SPP wavelength. We prepared IR140 and IR143 in different solvents, including diamethol and benzene alcohol, incorporated these game materials into silver plasmonic crystals, and demonstrated the tunability of the lasing wavelength. To conclude, we designed and realized a plasma laser with a unidirectional emission, and the wavelength can be modulated by the dielectric environment. We developed a simple and scalable fabrication technique based on template stripping to produce uniform 2D plasmonic crystals. We demonstrated that 2D plasmonic crystals provide a platform to screen material combinations for new classes of plasma nanolasers. We would like to acknowledge the funding from National Science Foundation, the fabrication and characterization facilities provided by IPAC and NUFAB at Northwestern University. We acknowledge Quest at Northwestern University for computational resources. Thank you for your interest in our work, and we appreciate your time in listening to our presentation.